Hello friends, welcome back to my YouTube channel. In this video, which is 36th part of my discussion on distillation, I will be starting my discussion on Ponchon-Savarit method. In the previous video, I completed my discussion on the McAfee method, and from now onwards, I will be starting my discussion on Ponchon-Savarit method. Ponchon-Savarit method. This video is an introductory video where the method will be introduced to you, and in coming videos we will talk more about this particular method, Ponchon-Savarit method. So let us begin the discussion. Let us know the basic information about this method, the basic information regarding the Ponchon-Savarit method. Ponchon-Savarit method, it is a rigorous graphical method that is used to find. So now I'm using this word rigorous to describe this method, because if you compare this with the McAfee method, it is more rigorous. Plus, it is also a graphical method. So that's why I'm saying a rigorous graphical method used to find the number of ideal, theoretical, or equilibrium stages to achieve the desired separation by fractionation. So a rigorous graphical method, and what is its application? It is used to find the number of ideal, or you can say theoretically, or you can say equilibrium stages that are required to achieve the desired separation by fractionation. And what is fractionation? Fractionation is a stage-wise distillation that is carried out in a tray column. You know this. Fractionation, it is a stage-wise distillation that is carried out in tray columns. So as was the use of McAfee method, the Ponchon-Savarit method is also used to find the number of ideal stages. But as compared to McAfee method, it is more rigorous, and that's why it is going to give more accurate results. So if you compare this with the McAfee method, whatever limitations were there with the McAfee method, all those limitations will be overcome in this method. Okay. So in simple words, we can define, or we can describe Ponchon-Savarit method as a rigorous graphical method that is used to find the number of ideal, theoretical, or equilibrium stages in a fractionating column to achieve the desired separation. The simplifying assumptions that were used in the case of McAfee method, I have made a separate video on simplifying assumptions of the McAfee method. It is available on my YouTube channel. You please watch it. So those simplifying assumptions of the McAfee method, they are not required. They are not required in this case. Ponchon-Savarit method, the Ponchon-Savarit method, it does not use these simplifying assumptions. That is why it is more accurate. Instead of using simplifying assumptions, this method requires detailed enthalpy data. Detailed enthalpy data is required. And while using this data, one fact, and what is that fact? The fact is enthalpy of a mixture. Enthalpy of a mixture of more than two components, it changes with its composition. So as you move from one tray to the other in the tray column, the enthalpy of the mixture is going to change. Why it is going to change? Because composition changes, and enthalpy of that mixture will change with its composition. So a detailed enthalpy data is required for the use of the Ponchon-Savarit method, and In this case, the change in enthalpy of a mixture with its composition, it is utilized in finding out the number of stages. What does it use? It uses the following things. It uses material balances, it uses energy balances, and it also uses VLE data. So it uses material balances are used in this method, energy balances are used in this method, and even the VLE data, vapor liquid equilibrium data, that is also used in this method. And that's why this method, it is more accurate than the McApthilly method. So all the limitations associated with the McApthilly method, I have discussed limitations of McApthilly method in my previous video. You please watch that. What are the limitations? You cannot use McApthilly method when the relative volatility is less than 1.3 or it is greater than 5. You cannot use McApthilly method if the reflux ratio is less than 1.1 times the minimum reflux ratio. You cannot use the McApthilly method if the number of theoretical stages is greater than 25. So all those limitations will not exist in the case of the Ponchon-Savarit method. Okay, so the Ponchon-Savarit method, it uses material balances, it uses energy balances, it also uses the VLE data, and that's why it is more accurate than the McApthilly method, and all limitations of the McApthilly method are overcome if you use the Ponchon-Savarit method. So what you have to remember, first thing is, it is a rigorous method, it is a graphical method, it is used to find the number of ideal equilibrium or theoretical stages in a fractionating column. Simplifying assumptions used in the McApthilly method are not required in this case. Detailed enthalpy data is required. The change of enthalpy of a mixture with its composition, it is utilized in this method. It uses material balances, it uses energy balances, and it also uses the VLE data. Therefore, it is more accurate as compared to that of the McApthilly method. Then the method, it make use of the following diagrams. If you remember, McApthilly method uses the distribution diagram. Now let us understand, or let us know which diagrams are used in this method. First, it uses the distribution diagram, and it also uses the enthalpy concentration diagram is also used in this method. So we need both the distribution diagram and the enthalpy concentration diagram in the Ponchon-Savarit method. So both, if you have to talk about this diagram, both the diagrams, they represent VLE data. They represent the VLE data, but in different ways. I'm going to talk about it shortly. I have discussed it in my previous videos. In this video also, I'm going to discuss those diagrams briefly. The point is, in the Ponchon-Savarit method, we need the distribution diagram, we need the enthalpy concentration diagram. Both these diagrams are different ways of representing the VLE data. Now, let us consider, in our discussion, we are going to consider a binary system as usual, a binary system of two components. Which are these two components? Component A and component B. A is the more volatile component. That is, it has a lower boiling point at the given pressure, and it has a higher pressure at the given higher vapor pressure at the given temperature. So A is the more volatile component. Now, the distribution diagram, what is this? It is a plot of X versus Y. What is X and what is Y? X and Y, these are mole fractions of A in the liquid and vapor phases respectively. And the liquid and vapor phases that we are talking about, they are in equilibrium with each other. So we are talking about mole fractions of A in the liquid and vapor phases when these phases are in equilibrium with each other. Then what is done? X, that is mole fraction of A in the liquid phase, it is plotted on the x-axis, and Y, that is mole fraction of A in the vapor phase, it is plotted on the x-axis. And what is the enthalpy concentration diagram? This is plot of HL versus X, that is enthalpy of liquid phase versus mole fraction of A in the liquid phase, and Hg versus Y. What is Hg? Hg is the enthalpy, molar enthalpy of the vapor phase versus mole fraction of A in it. So HL is the enthalpy of saturated liquid again, and Hg is the enthalpy of saturated vapor. So you plot saturated enthalpy of saturated liquid versus X, and enthalpy of saturated vapor versus Y on the same plot, and the resulting diagram is then the enthalpy concentration diagram. I have already discussed in my video on energy balance for atypical tray column. I am giving link to that video. You please refer that. Okay. So over here, now we know we need two diagrams. We need the distribution diagram, and we also need the enthalpy concentration diagram. And for the case of a binary system of components A and B, what is the distribution diagram, how it is obtained, I have told, and then how to get the enthalpy concentration diagram, that also I have told. So HL and Hg, what is the plot? This enthalpies, enthalpy of saturated liquid and enthalpy of saturated vapor, they are plotted on the y-axis, whereas mole fractions X and Y, they are plotted on the x-axis. Small x is mole fraction of A in the in the liquid phase, and Y is mole fraction of A in the vapor phase. So now let us look at the distribution diagram. So as I said, as we understood, distribution diagram is plot of X versus Y. So it is a square plot, that is the scale on the two axes, that is x-axis and y-axis, it is same. So small x, that is mole fraction of A, mole fraction of more volatile component, that is plotted on the x-axis, and Y, mole fraction of A in the vapor phase, it is plotted on the y-axis. And then for reference, we are going to draw the diagonal line and the curve. The plot of the equilibrium values will give us this equilibrium curve. So every point, if you consider any point on the curve, for example, this point, then y corresponding to this point, let me call it as y star, and x corresponding to this point, let me call this as x star. So in this case, y star and x star, they are in equilibrium with each other. That is, in short, the curve is a result of plot of equilibrium concentrations. That's why we are calling this curve as the equilibrium curve. So distribution diagram is simple. You are plotting concentrations of the more volatile component in the two phases against each other when the two phases are in equilibrium with each other. I hope this is clear to you. If you have any doubts, you can mention them in the comment section. Okay, now let us look at the enthalpy concentration diagram. So what is done in this case? You are plotting enthalpies on the y-axis and concentrations, that is mole fraction in this case, on the x-axis. So HL and Hg, enthalpies of the liquid phase and enthalpies of the vapor phase, they are plotted on the y-axis, and X and Y, that is mole fraction of the more volatile component in liquid and vapor phases, they are plotted on the x-axis. So this end, it represents X is equal to 0 and Y is equal to 0. So what is the meaning of this? So when you have a mixture of two components, A and B, in the liquid phase, and you have the same two components in the vapor phase. So if X is equal to 0, that means mole fraction of A in the liquid phase is 0. That is, there is no A in the liquid phase. And if Y is equal to 0, that means mole fraction of A in the vapor phase is 0. That is, the vapor phase does not contain A in it. The point is, at this end, where X is 0 and Y is 0, this end, it represents pure B. There is no A in the mixture if you are at this end. So that's why this end represents pure B. Now look at the other end. X is equal to 1 and Y is equal to 1. That means, again, if you have to discuss this with the help of this particular example. So in this case, let me erase everything so that I can write new example. Okay, so at this end, we are talking about the other end where X is 1 and Y is 1. So again, you have two components in the liquid phase and the same two components in vapor phase. So at the end where X is 1 and Y is 1, that means there is no B in it. There is only one component at that end, and that is A. So the point is, this end, it represents pure A. This end where X is 0, Y is 0, this end represents pure B. And when X is equal to 1 and Y is equal to 1, the other end, it represents pure A. Okay, so to get the enthalpy concentration diagram, enthalpies are plotted on the y-axis and corresponding mole fractions, they are plotted on the x-axis. So if you plot enthalpies of vapor phase versus Y, you get a curve. So this is Hg versus Y curve. This is result of plot of Hg versus Y. Whereas you get a lower curve if you plot enthalpies of liquid versus X. And the difference between these two curves at the end, X is equal to 0, Y is equal to 0, which is representing pure A. This end gives this difference between the two curves. It will give molar latent heat of vaporization of pure D. And you can easily tell at this end, you'll be getting this end, since it represents pure A, the difference between the two curves, that distance will give you molar latent heat of vaporization of pure A. So this is how the enthalpy concentration diagram is plotted. I have discussed about it in my earlier video on the energy balance. Again, I have discussed it. If you have any doubt, if you have not understood any concept in this particular case, you can mention that in the comment section. So this is the second diagram, the enthalpy concentration diagram, which will be used in the Ponchon-Savarit method. So with this, I end my discussion for this small introduction to the Ponchon-Savarit method. What we have understood, Ponchon-Savarit method is a rigorous graphical method. It does not use any assumptions, simplifying assumptions, but instead of that, it uses detailed enthalpy data. It uses energy balances, material balances, VLE data. That's why it is more accurate than the McAfee method. All limitations of McAfee method, they are gone with the Ponchon-Savarit method. It uses distribution diagram, it uses enthalpy concentration diagram, and then I have briefly told you what are these diagrams. What is the distribution diagram, and then what is the enthalpy concentration diagram. So in my next videos, in my coming videos, I'll be discussing more about I'll be discussing in detail about the Ponchon-Savarit method. What is the theoretical background? What are the steps involved? And then I'll be solving some numericals based on the Ponchon-Savarit method. For this video, thanks for watching this video. Do subscribe to my channel if you have not done that. Tell your friends to subscribe to it. And if you have any doubts, you please mention them in the comment section. And don't forget to hit the bell icon so that you'll be notified as soon as I upload any new video. So in coming videos, I'll be talking more about Ponchon-Savarit method, as I said, and then other mass transfer on operations like liquid extraction, leaching, adsorption. So all these discussions will be important from the point of view of coming gate examination. So please do subscribe to my channel. If you have any doubts, you please mention them in the comment section. For now, have a nice day. Bye bye.